So friends, I'm going to start with preparations of carboxylic acid. These preparations will be divided into three different videos. In all, we'll be covering up about 6 different methods of preparing carboxylic acids, starting with primary alcohols and aldehydes. Right? We already have done this, but we would be once again doing these methods. The second is from alkyl benzenes and alkenes. So that's the second method that we would cover up. So these two would be covered up in the first video that we take up. And after that, in the next video, I would be talking about how to prepare carboxylic acids from nitriles and amides. And then there is this one more method which is called Antistate Method. This method allows you to get a higher homolog of any carboxylic acid. So if you want to increase the carbon skeleton of any carboxylic acid, I think this is a good method. After which we have hydrolysis of acyl halides, anhydrides and esters, and towards the end we have this Koch reaction, which is a very special reaction done for olefins, and you can get carboxylic acids even by this method. So let us quickly begin with the first method of preparation, which is from alcohols and aldehydes. All right, let us first of all talk about how to get carboxylic acids from primary alcohols. Now, some of the reagents which you can use here are, they can be KMnO4. This can be used in acidic, alkaline, or even in neutral conditions. The other thing that you could probably use here is K2Cr2O7. Along with that, you generally use H2SO4. And the third reagent you could probably use for converting primary alcohols to carboxylic acids would be CrO3 and H2SO4. Here, this would be called Jones reagent because the solvent used here is aqueous acetone. So this is Jones reagent. Also very important. Let me put this here, right? So these are the three common, methods used for, conversion of primary alcohols to carboxylic acids, right? Now, let us first of all take up the general equation. I can take a primary alcohol like RCH2OH, and I can have, KMnO4 used. Now, remember, in acidic conditions, when you carry out such reactions, what happens is your alcohol, which is converted into carboxylic acid, like for example, if I consider this as H plus, right? What you get is RCOOH. Fine. But what exactly happens is this carboxylic acid which is produced here, right, it may start reacting with the unreacted alcohol, and because the condition is acidic, it may also lead to formation of esters. So here we always write that in acidic conditions, esters are produced as byproducts. So such reactions are preferred to be carried out in either alkaline conditions or neutral conditions. Now, when you perform such reactions in alkaline or neutral conditions, maybe we can take up something like this. This is like benzyl alcohol. And this benzyl alcohol, when treated with KMnO4 in alkaline conditions, you could probably, get C=O minus and K plus, right? The first thing you get is like C=O minus and K plus if KOH is used here. So I may directly put KOH. So in that case, you get K plus, and this needs to be then acidified. So once you acidify this, you end up in getting the corresponding acid. So this is your benzoic acid that you get. So basically, you always have to prefer producing, carboxylic acids from primary alcohols in either neutral conditions or, in alkaline conditions. But you should not use acidic conditions because that might lead to some byproduct formation. Yeah. So I think this is the first reaction. I can give you some more, some more examples. So let us first of all have this. You can take one more example here. We can take something like decanol, CH3, CH2 8 times, and CH2OH. What we have here is decanol, and even decanol can be treated in the same way. You can use alkaline KMnO4. I can put both the reactions together, and in the second part I can put H plus. I may directly get my product CH3, CH2 8 times, and then COOH. This is what you call as decanoic acid, right? So you end up in getting decanoic acid, and this is one more reaction, right? So I hope you've understood how to get carboxylic acids from primary alcohols. Now, as far as aldehydes are concerned, we've already taken this up, how aldehydes can be converted into carboxylic acids. But, any aldehyde, RCHO, apart from using all the above reagents, right, you can even have RCHO becoming RCOOH, even in presence of mild oxidizing conditions, like you can use Tollens reagent here. Tollens reagent is nothing but Ag in H3 2 times plus and OH minus. So you can use Tollens reagent, or you may use any one of the above mentioned conditions. All of them would lead to formation of carboxylic acid. So getting carboxylic acids from aldehydes would be quite simple. Let us put this as aldehyde, and let us call this as an acid. I hope you've understood how this goes, right? So this was our first preparation. We would be moving towards the next preparation now. All right, first of all, let us understand how carboxylic acids can be obtained from alkyl benzenes. Now, you know that any alkyl benzene can be treated with a number of oxidizing agents like KMnO4, used in generally, alkaline conditions, or even acidic KMnO4. Doesn't make much of a difference. So alkaline or acidic. Or you may use K2Cr2O7, potassium dichromate with H2SO4, or you may use dilute HNO3. So any one you can use, and it would lead to, aromatic carboxylic acid. Here, because you've taken benzene, right, this aromatic carboxylic acid every time, irrespective of what alkyl group you have, right, would give you COOH upon oxidation. So this is the primary product which is produced every time. So there is no change, right? Which would also mean that irrespective of the size of the alkyl chain, right, it would always be the same compound formed upon oxidation. Although these oxidations can be quite vigorous, right? You have to do some vigorous oxidation, but yes, you have the same product obtained. For example, I can show you that. We start with ethyl benzene, and you have KMnO4 and KOH, heat, and you can have H plus towards the end. Now this would finally give you only one product every time the same product gets formed, and that is your benzoic acid. So this was like ethyl benzene, and finally you get benzoic acid. So basically, such reactions, they can be quite simple and easy. You just have, irrespective of the chain length, every time you get the same product. I can give you one more option here. See, why would this happen? For example, you may take isopropyl benzene, which is many a times referred to as cumene. So, isopropyl benzene, many a times referred to as cumene, when treated with 1 KMnO4, and if I use H plus, doesn't make any difference then, so I don't have to then put 1 and just heat, I may end up in getting this. Once again, the same thing. Benzoic acid. See, the point is, as compared to the hydrogens which are present on the aromatic ring, the side chain hydrogens are always, and especially these benzylic hydrogens, are always more reactive. So when we talk about these benzylic hydrogens, they're always more reactive, and hence as long as you have a benzylic hydrogen, this reaction continues, right? However, if you don't have a benzylic hydrogen here, suppose you don't have a benzylic hydrogen here, we take up a tertiary alkyl group here. So if you take a tertiary alkyl group, with no benzylic hydrogen here, right? So here we say no benzylic hydrogen. In that case, the reaction would not take place, and there would be no reaction. So if I put KMnO4 and H plus and heat, I may write no reaction. So what do we conclude here? We conclude that if the oxidation of alkyl benzene is supposed to take place, then there should be a minimum of one benzylic hydrogen present. If there is no benzylic hydrogen present, then there would be no reaction. Now, let us get an idea about what would happen if you have a substituent on the ring. For example, if you compare the reactivities of two different, alkyl benzenes, one is simple, methyl benzene, and one is benzene ring having a nitro group. Now remember one thing, if I ask you about the reactivity of these two, right? If I ask you both of them are subjected to oxidation, which of the two would react faster? So here you find that presence of electron withdrawing group always increases the reactivity of alkyl group. So presence of electron withdrawing group increases the reactivity at benzylic carbon. And hence reactivity towards oxidizing agents increases. So remember one thing, when you so this basically is this is going to be less reactive, and this is going to be more reactive. So you have to know this, that by putting an electron withdrawing group, you can always increase the acidity, increase the capacity of any group to undergo oxidation. I'm sorry for this. Yeah. All right. So I think you have to know this, right? There are quite a few other examples that I can give you, right? I can have one more example that I can show you. So this is a ring with a nitro group, and this is another ring, right? Now, if I subject this ring for oxidation, KMnO4 and H plus, and heat, then there would be oxidation taking place here, and you find that your product, the side chain, or the ring where you don't have nitro, it gets very easily oxidized, and so the ring which has nitro remains intact, and you have two COOH groups. Okay, so this is something which you have to know. There could have been reaction either ways. There could have been reactions on both the sides. The same reaction would have happened to this bonds also, like these bonds would have broken, and I'm sorry, I think these bonds are broken. I'm sorry, COOH and COOH. So I can show you this. It is actually these bonds which break down and not these bonds, so we can at least remove them. Not these bonds. Yeah. So you can have there are two possibilities. Either these bonds get broken or these bonds get broken, but nitro present on the ring would increase the reactivity of the other ring, right? And that is why we have this. Okay, so electron withdrawing group would increase the reactivity of the carbons which are directly connected to the aromatic ring. So these are the carbons which are connected to the aromatic ring, and therefore their reactivity would increase, and that is where the oxidation takes place, right? So yeah, so this is about the reaction. Now we take up how reaction with alkenes occur. Now that's pretty simple. When you take an alkene, any alkene like this, the same components can be used here. You can use K2Cr2O7 plus H2SO4, or you can use KMNO4 in acidic conditions. You know that the chain breaks here, right? And both the components get converted into corresponding acids, which means you get RCOOH plus R-COOH. The same reaction can be expected, and same products can be obtained if we use ozone in first case, and in second case, see, after doing ozonolysis, you get aldehydes in first case, but if you perform hydrolysis, oxidative hydrolysis, not the reductive hydrolysis, so we don't use zinc, oxidative hydrolysis, in that case we once again get the same products. So you can use any one of these oxidizing agents, and if you're using ozone for oxidation of alkenes, you need to see to it that the hydrolysis is performed in oxidative conditions and not the reductive conditions. That's it, right? So we've done two methods. In my next video, I would be posting two more methods of producing carboxylic acids.